All right. Hi, everybody. I suppose we can start. I wanted to start off with I guess I wanted to start off with an announcement. So I'm not really sure if this has been conveyed to you, but the reason why we had to have a virtual class here is because apparently I was made aware by Peter, I believe, Luasi, yesterday, the course reps anyway, they made us aware of the fact that apparently on Fridays the venue has a different class running right from there, and I don't know if you've been affected by this, but apparently for some courses there've been very emotional arguments about venues, especially for venues. Is it in law school or something like that? And I generally am not a confrontational person. I prefer to avoid those things. So what I am planning to do is to reach out to Mrs. Kumar, who coordinates venues on our behalf, so that we seek clarification from the assistant dean if this biology class is actually supposed to be scheduled there. Okay. But in the meantime, I mean, class is going to continue. And just as well, I think it's a good thing that we are mostly looking at stuff that is a bit hands-on. And because it's hands-on stuff, you generally would want to be sitting behind a computer or something. I would if I were you, actually. But at the very least, you'd be using Temax or something for you to you'd be using Temax for you to what is this? Reload. You'll be using Temax here for you to be able to follow through with what we are doing, right? I would do that if I were you, to be honest. Otherwise, these things will not make a lot of sense. And we've actually barely started to scratch the surface here. But anyways, so we're going to continue our discussion. Reminder that we are wanting to finish up our discussion of some of these best packages that we're going to be using, and we've been looking at NumPy. At least we're looking at NumPy. We're getting to a stage where we were looking at is it operations, so element-wise operations. There's something interesting about these element-wise operations. They're called element-wise operations because they essentially are applied on all elements in your NumPy array, ideally, right? It's a good thing, I guess. And then I hinted at the fact that, quite important, because one of the things we're going to be doing here is using the dot product, or matrix multiplication, if you will. And I mentioned that nowhere here, by the way, are we using the asterisk, is it? We're using the @ sign, okay, for us to compute the dot product. So take note of that. If you're looking at performing element-wise operation, you're obviously using the asterisk. But when you're performing classical matrix multiplication, you use the @ sign. And true to that, actually, we kind of we did this, is it? If we do probably didn't, but we can do this, right? If we do an import, NumPy as NP, and then we create a NumPy array A, which is going to be equal to np.array. Then we feed this so use something simple here, 1, 2, 3. Then we create var b, which is np.array. Then we continue off from 4, 5, 6. If we do var ab asterisk var b, what we get is a NumPy array object which comprises of the results of performing element-wise multiplication, right? So it's 1 by 4 gives us 4, 2 by 5 gives us 10, 3 by 6 gives us 18, right? So it's element-wise multiplication. However, if we are looking at getting dot product, right? Classical matrix of multiplication, what we do is we'll do var A multiplied by var B, ideally, right? So we get this value here. Anyhow, hopefully this is making sense. I don't know if you've noticed what is happening here. I don't know if you still remember this. I think you did this in grade 5 or something. But when you're performing the dot product, as the name suggests, what you're doing is what? You're doing, but what's happening? There we go. What you're doing is this, is it? It's like you're performing 1 by 4, right? It's like you're doing 1 by 4 plus 2 by 5. So 1 by 4 plus 2 by 5, and then plus 3 by 6, is it? Like so. So that you have your 4 plus 10, 4 plus 10 plus 18, which gives you this number here, you see. Right? I don't know if this is making sense. There must have been a course you did. I'm not sure. Did you did? When did you do linear algebra? There was a course, right? Yeah, don't know. When did you do linear algebra, you guys? Oh yeah, I don't know. Okay. Yeah. Again, just showcasing how matrix multiplication will actually be done here. Now, there's more here, right? More stuff. It turns out that you can actually reshape and transpose these NumPy array objects. Reshaping changes the dimensions without necessarily changing the data itself, right? So you could have the 1D kind of object that can be reshaped into something else, right? And then transpose. I think you did this again in first year. I don't know if it's second year in your IT course or something. Transpose essentially converts your rows into your columns and your columns into rows. Quite a popular kind of feature here. If you have, I believe you've done this in Excel. There should be a way to transpose. Is it? If you have, let's say male, female, or something like that, and then you have 1 and 2. Is it 1 and 2? I don't know if this is a good enough example. You can transpose this, right? In Excel or in a spreadsheet application, when you copy, you can do a paste special and then you do a transpose, right? So it converts stuff like this, something. So in essence, this is what this thing does. And again, if we were to look at an example of this NumPy, assuming we have an object that has these 5 elements, in this particular case, I'm just going to copy paste them here so that we quickly do this. Assuming we have this NumPy array object, I'll call it C actually. You notice here, if we check the dimensions of C here, this is a 1D array object, is it? We can do also fancy things like check the shape here, right? And we see that this thing only has 1 row, right? And it has 6 columns ideally, right? Now the idea behind transpose is if let's say we wanted to change the dimensions of this, what we can do is we can just invoke the reshape function, right? Reshape, and in fact, what you can do with the reshape function is you can take a look at the help manual and see the sort of arguments that it expects and what you get back ideally, right? So we can reshape. We can reshape this. Reshape this. In this particular case, we want to reshape it in such a way that we have, if you look at ending here, we want to reshape it in such a way that we have a 2-dimensional object instead, right? So in this particular case, the 2-dimensional object which has, 2 rows, each with 3 elements, I guess, so 2 by 3 ideally. Okay, again, if we check the shape here, obviously it gives away the fact that this is a 2 by, we've created a 2 by 2x3 matrix, originally represented as 1D, ideally. Transpose, like I said, ideally just flips the axes, if you will, or the dimensions. So again, looking at this example, if we have a matrix, copy this, a matrix V, V var underbar M, like this, which obviously has what? How many dimensions are these? This is 2 dimension, and then the shape is 2x3, right? 1, 2, 1, 2, 3, 1, 2, 3. So it's a 2x3 matrix. And what we want to do in this particular example is we just want to transpose this, right? You notice that transpose doesn't really, it doesn't expect any sort of arguments, because all you're doing is you want to swap what is currently represented as columns into rows and rows as columns. So just call uppercase T here on the matrix, and then this is what we get back. Again, you notice that if we come back to M here and see the contents of M and do a transpose, all we are doing, I'm just going to copy paste these things here so that it's a lot easier for us to understand. All we are doing is we are converting these things into rows, is it? 0, 3, 1, 4, 2, 5. And obviously the opposite is true, right? So we can change this if we want to, right? And I hope it works. I think it should be able to work. So we have var underbar m dot t, right? We get back the original, the original matrix. Again, we can probably run, what returns afterwards obviously is numpy. It's a numpy array object, an ND array object ideally. And we can still, if it's an ND array object, we can still run all those different methods we've been discussing, right? Shape, ND, size. What's particularly interesting here is that the size remains the same, is it? Irrespective of how you transpose the matrix itself, it remains exactly the same. In fact, reshaping has a similar effect, right? When you are reshaping, you have the same number of objects, right? It's the same elements. So it's still 6, ideally. Okay, this is trivial stuff. It's not that difficult. What's important is you know what you're calling. If it's functions or attributes, if it's functions, you need to know exactly types of parameters that you have got to invoke that particular function with. In other instances, like when you're using transpose, yes, as an attribute, right? You're not feeding it any parameters again. I wonder if we can get back, if we do var m dot t, I wonder if there's any useful stuff here associated with the t, the transpose. Probably not. That's okay. That is okay. I guess I'm looking for t here. M dot t. Yeah, so you can't even find it here, but I guess you'd probably be able to. I don't know if you'd be able to find this attribute somewhere here or something like that. Or let's check the type here in the array object. Anyways, yeah, so that's reshaping and transposing, and then of course, I mean, you'd find yourself wanting to flatten a multi-dimensional array, for instance, so you can invoke the flatten function. What it does is it converts your multi-dimensional array, in this particular case, a 2-dimensional array, into a 1D numpy array object. So observe, we have this 2-dimensional object, and we know it's 2-dimensional because we can evoke ndim, shows this is 2, the shape is 2x3. If we want to flatten this, what we do is we evoke we invoke the flatten function. It doesn't accept any parameters, right? And then what it does is it just converts this 1D object into this 2D object into 1D. Again, we can check the shape here. It's obviously going to be 6 comma nothing, right? Or we can check the ending here to confirm that it's actually been converted from the previously 1D array object into the previous 2D array object into 1D array object, ideally. Okay, again, if we're to link this to our discussion, in case you're wondering, well, I mean, why are we even looking at this, Lighton? Well, it turns out that a number of these operations are going to be tremendously useful as we are preparing our Vertex data, right, for OpenGL. You know, the data is going to be formatted in a certain specific way. More on this when we start looking at PyOpenGL. Again, just a visual representation of what happens when you're reshaping and when you're transposing things, right? Unless if there are any questions, any thoughts about NumPy, or maybe just have a brief discussion here of how NumPy is going to be used with PyOpenGL. So what you'll notice, especially in lecture series number 5, I believe it is, or I think when we start looking at part number 3 or something, one of the things we're going to be doing is we'll be, for instance, moving objects, right, from model space to word space, if you remember this discussion from our logical pipeline. And we do this, turns out, by leveraging matrix transformations, right? So you will see us use NumPy to create and apply, you know, transformation matrices, ideally. Just an example of how we would do translation. If you remember, with translation, again, I don't know how much of this you remember. This is word space, right, from your logical pipeline there. And we say that translation, in essence, just involves moving, is it? You're moving an object from position A to maybe position A plus N or something like that, right? So what you see us doing here is using a translation matrix, a 4x4 translation matrix like this, for instance, right? You will notice that we obsess a lot about the data type. I think we already made mention of the fact that OpenGL expects us to use float32 as a data type. So we've got to explicitly use this data type because the default is 4064, if you remember. Right. So we'll be using this translation matrix. We'll mention we'll provide more details to this later on. But in essence, what we'll be doing is, if let's say we want to move, if we want to move, an object with position tx, ty, and tz, before we can actually move, we will need to convert this into a 4x4 matrix using this format here. And then for rotation, again, if you remember rotation, we said all you're doing is rotation is you're flipping your object somehow, right? You're not necessarily changing the shape, just like you're not changing the shape with translation, but you're just changing the orientation. So you may be interested in spinning it or something. So you will notice that we'll be using a function like rotate z in this particular case, right? Where our interest will be to return, again, it's a 4x4 NumPy array object, ideally, with the appropriate data type of float32. Again, just an example of scaling as well, right? So if we wanted to scale x, y, and z coordinate with the scale factor s, what we'll be doing is we'll be interested in returning a 4x4 matrix, which is formatted as shown here. Right? Notice that we only have values in the diagonal. The diagonal place values of this 4x4 matrix, ideally. Similar to what we introduced as an identity matrix, if you remember, right? We said an identity matrix only has values in the diagonal position of the matrix. Okay, again, just to showcase application of NumPy, like in action here, let's say we wanted to, this example just showcases preparation of Vertex data for a triangle, for instance. Simple stuff here. We are interested in specifying 2 key attributes of our 3 vertices. So we have 3 vertices, V0, V1, and V2. And what we are doing is we are representing these vertices in such a way that the first three values for each vertex represent your x, y, z coordinates. And then the last remaining three represent the RGB values. Yeah, because remember, one of the key attributes associated with the vertex is the color, right, associated with that vertex, represented by RGB. Because we are working in NDC space, if you remember, the values that we are providing, in as much as we may be working with different sort of coordinates, let's say model space, but when we're working with these coordinate systems at this stage, we are assuming that we're working in NDC space. So all of these x, y, z coordinate values have got to range from -1 all the way up to +1, right? So v naught, for instance, in this case, is at position -0.5, -0.5, that's x, y, and then 0 in the z coordinate. A nice way of visualizing this is you can assume that the center of your screen, for instance, would be 0, meaning that v0 will be, negative direction is to your left here, so you're going to move halfway through to the left, right, somewhere here. And then your y coordinate is negative as well, so negative is going down here, so it's -5 is halfway through down here. So your point v naught to be somewhere here, right? And v naught here is red because we have 1, 0, 0, is it, RGB. So we're saying that the R value of our color space ideally has the maximum value. All we're doing, by the way, in terms of the colors is we're saying RGB. We're saying, assuming we are working with 8-bit representation, 8-bit depth ideally, the expectation is that the values for red would range from 0 to 255, right? 255. The value for green would be 0 to 255. It can be any value between 0 and 255. And for blue as well, it's 0 to 255. Now, what we've done here, if you notice, is we're saying we are scaling. We are scaling the color values so that they range from 0 to 1. If you're scaling from 0 to 1 here, it's almost like you're just going to divide the minimum and the maximum values by 255, is it? So it's like 0, you're ranging from 0 divided by 255 all the way up to 255 divided by 0. So if you have, then you have something like this, comma, this, comma, this, ideally. And so if we are saying that our vertex v0 has the values -0.5, comma, -0.5, comma, 0.0, comma, 1.0, comma, 0.0, comma, 0.0, in essence, what we are saying is that this is what we're saying here, right? This is the x coordinate. This is your y. This is your z. And then this is your r. This is your g. And then this is your, let's see, delete this here. Blue, ideally. No, so this is divided by, thanks for that. This is 0 divided by 255. This is we're scaling by 255. So it's not 0 divided 0. Thanks for that. No, that was it. So it says 2. You're dividing everything by 255. So this would be 255 here. Thanks for that. All right. Yeah. So you'll be seeing these sort of things, right? And so you notice here we are essentially creating. I want to argue here that there's different ways of doing this, right? In this particular case, it's a very weird thing here. We may have, I think I've mixed up stuff here. This is supposed to be corrected somehow. Maybe not. I mean, we could work with this. I mean, if it's contiguous values, it's fine as well. I just realized something. Ideally, this would make a lot of sense, I guess, if or maybe not. I mean, this could be viewed as a 2x2 matrix, is it? Where your vertex positions each wrapped into their own are each wrapped into their own. So we do this here. Vertices into their own list of sorts, right? I don't know if this is making sense here. Or, I mean, this would probably work as well. It's just that it would, I want to argue that this would require a little bit of effort, right? Because it's a 1D object idea, I think, endian. It's a one-dimensional object. In essence, you're saying you're just going to have a contiguous values of each vertex is being represented by six characteristics, right? X, Y, Z, R, G, B. But so if we create something that is just continuous like this, you'd have to figure out a way of just extracting the positions that you're interested in. But if you were to wrap these into separate lists, you'd say it's a two-dimensional object. What I mean is this: it's a two-dimensional object which is created in such a way that you're wrapping things like this. How does it work here? If I just copy paste it, this is much better, is it? Because each one of these, right, in this two-dimension, yeah, and each one of these lists here is holding the attributes associated with the vertex itself. Anyway, so this is what we would do, right? We are creating vertices associated with a triangle that would be interested in rendering idea, right? Again, if we were to copy this, I guess, which is fine. This is 1D array object. You'd say, I'm just going to copy paste this. You can extract information associated with all those different characteristics that we looked at, right? So we can check the shape, right? So var vertex shape, in essence, just returns the total number of items here is 6 by 3, right? Because each vertex is represented by 3 attributes. 3 for the coordinates and the other 3 for the color scheme being used. Okay. The item size is it's going to show you apparently item size, and I didn't know about item size, but actually item size. I want to get a sense of what this is about here. 4. I'm genuinely not, honestly not aware about item size. I didn't know that 4 bytes per element. I guess if this is the case, if it's 4 bytes per element, right, and we can probably do a little bit of debugging, right? Item size. So if the size of each item is 4, then we expect what? We expect the size of the entire array object to be something like 72 bytes, is it? And so if we evoke in here, if we do n byte, I think it is n byte. So we get 72. Okay, so that makes sense. Yeah. So telling us here that you can, there's n bytes. You can actually compute. You can figure out the size of each element ideally by running item size ideally. And then n bytes to figure out the size of this entire NumPy array object. Okay. And then what we're doing here is we say, well, we can reshape this, right? Apparently. And reshaping, I guess, reshaping gives us something similar to how I would, I guess, my preference in terms of representing these 3 points, right? Rather than have a one-dimensional array object that has just 8 elements, I would much rather I feed it to, or I create the vertices of the triangle by making a distinction between all the 3 the 3 vertex positions, ideally. This is intriguing, I guess. Okay, unless if there are any questions here, just to mention that we shall be using the vertices.n bytes to tell OpenGL how much memory to allocate, right? Because we're working at a very low level. I think I see a question. I don't know if there are any questions before we move on to the next, the next, I'm looking at the comments here before we look at Pygame. I'm looking at the comments. This is interesting here. Somebody's saying, okay, can't see my screen here. I can see my screen. You want to maybe try and exit and log back in. I'm logged on my mobile device. I use this to check if you can see what's on my screen. So I know you can. And then there's a comment here saying, would you consider using a code editor next time, please? The terminal is cool, but I find it difficult to follow. So, yeah, there are a lot of people that apparently can see my screen here. I think you should be able to see my screen, right? Can you see? Are there a lot of other people that can't see my screen? Thumbs up if you can see my screen. So there are people that can see my screen. I don't know if you're using the same network or something, but yeah, quite a number of them. Yeah, you want to try and yeah, I don't know about that. I mean, the best I can do is I can reshare it or something, and hopefully this time around a lot of people will be able to see. So can you again thumbs up if you can see and thumbs down if you can't or something like that? Yeah. So if you can't see, I don't know if all of you are on the same network or something like that. I don't know. You want to maybe try and exit and log back in or something. There's quite a number of people that can't. Yeah, I have no idea what could be going on here. But certainly I can see my screen on my mobile device, right? And I usually use that to yeah. So I want to try exiting and logging back in. Somebody just commented here. Donald just says he was able to think. So there's something interesting, right? Somebody is saying, so if you can't see my screen, exit and then join us again, right? You should be able to see my screen. There's somebody who is suggesting that they don't use the terminal. So the reason I use the terminal, especially for what we're doing right now, is it's a quicker way of testing out some of these things, right? But I will try and use going forward. I will use a lot of what do you call this? A lot of Visual Studio Code, if anything. Yeah. Okay. So on with it then. And there's a question here saying, if you use X, Y, Z, X, Y, Z, R, G, B, does it mean you cannot access both CAL and Vertex data using indexing at the same time? Well, I don't know what exactly you mean, right? But you could actually, because here's the thing, if you reshape it like this, right? If we reshaped it now, and notice once we reshape this, it becomes what? A two-dimensional array. If you look at the shape here, it's like 3 by 6, right? So meaning that we have 3 positions, each with 6 attributes. If we wanted to get the attributes associated with the very first vertex, V0, I guess in this particular case, which is the first one, all we'll do is, after reshaping, we'll just say we want the vertex at position 0 or something like that. And what you have here is, again, if you check in ndim, this is a one-dimensional array object, right? Shape, right? Or just the 6 attributes. And then from here, we actually do have access to X, Y, Z, R, GB, or something like that. I don't know if this is making sense here. Okay, so on with it then. We're going to proceed, and it turns out that what we are looking at next is Pygame, right? Now, we already know how to install Pygame. In case you've forgotten, all you have to do is, assuming you're using an environment, all you have to do is you do a pip. If you're using an environment like myself, you just do a pip install Pygame. And people will be able to install Pygame on your behalf. And if you do a pip list, you'll be able to see that you have access to Pygame. Is it? That you have access to Pygame. In addition, we said that you can actually do a test. Is it? Pygame is quite interesting, because the way that you tell that you've successfully installed Pygame is you get a message once you do an import Pygame, right? Yeah, this thing here, hello from the Pygame community or something. Whereas with NumPy, you don't get anything back. And as they say, no news is good news, is it? So if I say import NumPy, there's no news here, meaning that everything is fine, right? But if you get back an error, then there's something wrong there. Anyways, so you do that, and then in the event that you want to find out additional details about Pygame, there's a whole website dedicated to this. So if you just go to Pygame here, but if you just go to pygame.org, you'll be able to find tutorials there, you know, a whole slew of things. Our interest, I want to mention up front here, our interest is just to use Pygame as a canvas, right? So we actually, we are underutilizing Pygame, okay? In any case, so what Pygame is going to do is it will provide us with a bridge between the code we're going to be writing, right? Let's say you're defining your vertices and you want to draw a triangle, for instance, the operating system, and also the OpenGL API. And really we'll be using Pygame, for instance, to create a window, right? So we will use it to have the operating system create a canvas for us using given dimensions, right? So for instance, 800 by 600. And if you remember our discussion from lecture series number 2, when we have something like 800 by 600, in essence, we want to be able to draw something. A nice thing about this is something that is going to help us render pixels, 800 pixels, right, horizontally, and 600 vertically. Now this is arbitrary, right? For some, what do you call this? For some screen sizes, this would be like you're underutilizing the window or the resolution of your, I want to say your device, right? In my case, for instance, I have what is like zero render or something. I can use zero render to try and gain a sense of the resolution of my screen, right? And I don't know if I can see primary here, normal and stuff. So my computer, my T14, my ThinkPad 213 has a resolution of 1920 by 1080, right? So in other words, it's almost like right, primary, pay attention to this. It's almost like what I would be doing is I would be creating a window that in fact, I think I have something here that I can use as an example. Just going to open it up. I have some sample code that we're going to use as a basis to discuss this, right? So if I create a display that has a resolution of 800 by 600, like in this case, and I run this, what is ultimately going to happen is one minimum. What is ultimately going to happen is, where is it? Come on. Where is it? I'm looking for the window here. I'm just going to exit here and then run it again. Sorry about that. Okay, command not found. I have got to, first of all, activate the, I've got to activate the environment, and then I'll run Python here, you know, just record one minimum or something like that. Right, so if you notice, right, I'm just creating this window here. I don't know if you can see the window. Just going to exit here so that you see this thing here. It's created at the center because from left to right here, from 0 here, I can lay out 1900 and what? If you look at my output here, I don't know what it is here, but I'll just zero in. I can lay out pixels that would be 1920 horizontally, and then 1080 vertically. So if I use 800 by 600, I'm just using a fraction of this resolution that I have. But anyway, so this is what we're going to be doing, ideally, right? Easy enough. And then also, so we'll be, Pygame is going to enable us request, insofar as the OpenGL context is concerned, it will help us request an OpenGL capable drawing surface from the graphics drivers, right? And it turns out that this context, this OpenGL context, is what will help, is what is going to enable us to hold all the OpenGL state, right? So the shaders, the buffers, and any other current settings that would have defined in our code ideally. More importantly, and this is important for all types of window-based applications, is that you'd want to handle certain types of events. Like, for instance, if I have I have this screen. I want to be able to close it, right, by clicking this X button here to the top right. So if I click on it, it should close, right? I'm handling that event. In addition, if let's say if I've done the right thing here and the user presses the escape key, I want to be able to handle those events, because we know that if somebody presses escape, what they would want to do is to implicitly close the window or something, right? So Pygame will help us, handle these events. So capture user input, so keyboard events and mouse events. So you move your mouse and then you click the X button, you'll press the escape key or something like that. And then buffer swapping as well. So it's going to manage the double buffering mechanism for smooth animation in instances where we want to be able to clear the screen before we draw, for instance. And it turns out that, without Pygame, what would have had to do is would have to write a platform-specific code that will create that window for us, right? And again, be able to handle those events ourselves. And if you remember, I think in your Java programming, you probably were introduced to this, right? Where you're writing events to, you're writing those events to be able to close a window if somebody clicks close, to maximize the window if somebody clicks maximize, to minimize it if somebody clicks minimize. But all of this is being done for us. It's abstracted for us by Pygame, not by OpenGL. Sorry. More importantly, though, Pygame will give us a cross-platform, beginner-friendly interface, right? Doesn't matter whether this is on Windows, Mac, or Linux. Ideally. Okay. So in terms of how it does this, right? There are a series of basic steps that you have got to follow for you to be able to achieve the things that I've just mentioned. The very first thing you have got to do is, and I think I have examples as well. The very first thing that you have got to do is you must initialize all Pygame modules ideally, right? So you'll notice once we start going through example code of how you create a window and how you handle these events, is one of the very first things you do is you evoke the init method, right, from Pygame. And so you do an import Pygame. There's no alias here. If you want to, you can do import Pygame as PG if you want to, but conventionally or putatively, you just do an import Pygame. And one of the very first things you see us do is we'll evoke the init method, right, by running pygame.init, so that we initialize everything. And then we also set the display mode. This will make sense when you look at example. We have got to set the clock here to control the frequency at which we are rendering what is on the window, what is being drawn ideally. Nice thing about this is what we introduce as our FPS, right? A frame rate per second or something. Frames per second, which is your frame rate. Yeah, so step one, you initialize, you set display mode, you create a clock to control the frame rate, you enter the main loop, where you're continuously, it's like you're simulating and you're animating anyways. So you're going into this loop up until a user explicitly decides that they want to quit. So in other words, what we'll be doing is we'll be writing code that will get into a continuous loop. We haven't drawn anything here. So we'll have drawn anything, and then we're going to a loop. We're going to a loop up to when the user presses the X button in the top left, or they press the escape key or something like that. Right. So 4-step process here. And it turns out that with step number 4, which is where the drawing is done, there are like sub-steps that you go through, right? So when you enter the main loop in step number 4, there are a series of steps that you follow, right? So you have to write code to process the events, right? So mouse presses or key presses and all those things. You have to, clear the screen. You notice that we'll be using gclear. I think I had mentioned gclear when we were briefly discussing the OpenGL API in lecture series number, is it 3 or this same lecture series number 4? I can't remember here. Again, in the main loop is where we'll be drawing the OpenGL content itself. So it could be like a triangle or something like that, right? Also be swapping buffers, right, using pygame.display.flip. And then we'll be able, you notice that we'll be able to control the frame rate using the clock itself. by just evoking the clock.tick function and indicating the frames per second. So maybe it's 30 frames per second, or it's 20 frames per second, or 18 frames per second, or something like that. Right, so it's easy enough. It's not difficult, actually. And the beauty is that irrespective of what you're drawing, the things that you're doing are more or less the same, right? With Pygame, you've got to handle events, right? You've got to, clear the screen, for instance, right? Specify the frame rate and all those things. Anyways, putting these things into perspective, the steps, step 1 all the way up to step 5 steps, by the way. With step 1, when we're initializing Pygame, what we're saying is that what we have got to do is we have got to first of all import Pygame. Obviously, it's the very first thing we do is import Pygame, and then this is going to be by convention, right? And then for us to initialize, right, we evoke the init method. So initialization is simple, really. And again, all you're doing is you're initializing all Pygame modules, the display, the font, the sound, and everything else. What is important is the initialization has got to be done before you perform any other Pygame function. So before you even start handling these events we're talking about, right? So you will notice in the code, for instance, in the case here that I will have something like this line number 6, right? Of course, I have the function here because I'm wrapping the initialization is being done in my main function. I have the function definition before this. But if I was writing this as spaghetti code, what I would do right after these import statements is I would just have pygame.init. Okay. So after we initialize Pygame, what we do is we then set the display mode. And fundamentally, what you're doing with the display mode is obviously you've got to specify the resolution in this particular case. The resolution is specified by indicating the width and the height. So 800 is the width, 600 is the height. It's worth mentioning that in this example code, what I'm doing is I'm defining a variable called display, which I am then using as an argument, right, in the pygame.display.set underbar mode function. So what in essence, what I could easily have done as well is I could have said, I'm just going to use this here. I know somebody is not happy that we're using this here, but what I could have done is I could have said, I don't want to do this, but rather what I want to do is I'm going to say what I would have done is I would have done this, right? I don't want to do this because what I can do is I can say pygame.display.set mode, and then in here is where I'll define my resolution. Is it 800, 600, like so? It's one and the same thing. It's just that I think it's cleaner when you're specifying a variable like display separately or something, right? And then you have double buff. I'm just going to undo this. Okay, quit without. Let me decide to. I don't know. Okay, so this display here, it's a tuple, if you remember your Python, right? Where you have the width and the height. You're specifying the window size here. In other words, it's the screen pixels, right? You remember our discussion of pixels? These dots that are going to be laid out, right? Left to right. So if we run this again, like so, yeah, left to right, 0. This is 0. This is 0 here. And then if we go all the way up to here, this is position 800, right? This is 0 here. If we go all the way up to down here, this is like position 800, right? Sorry, 600. So it's 800 by 600, ideally. Okay, so again, just to wrap it in here, your display is going to define or determine the viewport mapping, right, from NDC screen space. So here's the thing here. It's like remember in NDC space, we have everything from -1 to 1 or something. What is happening when you're defining this is you're saying you're going to, whatever it is you're going to be drawing is going to be rendered, or you're migrating from that -1 to 1 cube to something that is equivalent to what you've defined here, which is 800 by 600 in this particular case. And then these flags are just constants, ideally, right, which you'd manipulate using your bitwise OR operator in this particular case. So the OpenGL constant requests an OpenGL context. And it turns out without this flag, the OpenGL flag, Pygame will use its own 2D rendering. But what we want is to use OpenGL context ideally. Right? So how do we do this? We specify the constant OpenGL. And in case you're wondering, well, but where is this coming from, right? How did we just suddenly gain access to OpenGL? Observe, if again, I know people don't like this, but if I say import Pygame, and then let's see if we can do this. OpenGL, right? Nothing. However, if you do from pygame.locals, import everything. From pygame.locals, import everything like that, and I now print OpenGL. I have this. So these constants that seemingly are just popping out of nowhere are coming from here, right? Do you remember I mentioned that you can import in three main ways ideally. So you can say import Pygame as alias, or just import Pygame, or you can say I want to import everything, right, from somewhere. So in this particular case, I say we want to get everything from pygame.locals, ideally. If that makes sense, right? Again, if we want to check the constant, and by convention, right, this thing in all uppercase, and so if we print out double buff, be able to get back a double buff, a constant, right? Is it 2Fs or something? Double BUF. Oh, double BUF. I don't know why this is not coming up. Let me just double. Oh, here, right? Double buff. Yeah. So in case you'll be scratching your head, I'll share the code. If you'll be scratching your head trying to figure out where are these things coming from, these are coming from here. This second statement from pygame.locals. Import asterisk, ideally. Okay, so double buff, we enable double buffering, right? So we'll be drawing to a hidden back buffer, for instance, while the front buffer is being displayed, and then you can easily swap them here to simulate flickering or an animation, if you will. Yeah, and then there are a few other flags here, right? That you can combine with this. So things like resizable to allow the user to resize the window, for instance. And then full screen as well to create a full screen window, for instance. All right, I'm looking at the time here. There's a bit more here. We are going to continue this discussion tomorrow, right? We are meeting, I think, tentatively we are going to meet at is it 13 hours or something? I scheduled a class for 13 hours tomorrow and Sunday. We'll continue this discussion. Meantime, I shall upload this. I shall upload this thing here, just so you can already start going through this. This is your complete. It's not that complex. It's just 43 lines of code or something. I'll upload this so that you can already start playing around with this and understand the 5 steps we just discussed. Is it? You're initializing these things here. You're initializing, right? You're setting display mode. You're creating a clock to control the frame rate. You enter the main loop and then you exit, right? When you call Pygame quit or something. This is what we implemented in this this Python module file, which is 43 lines of code. Unless there are any questions, I'm transitioning to a different meeting. We can leave it at that, I guess. Any questions about this? Clarification needed? Sir, can you please upload the notes ASAP? Well, I mean, I think I've tried here to I've tried to do this, right? I mean, the notes are there on the Moodle. I know there are gaps in terms of the videos, but the videos are there. I'm going to do this for the benefit of those that may not be aware, because I know, right? Some of you don't access these resources. And the way I know is if I go to the playlist, right, that has the recordings, for instance. In fact, if I just look at the logs in the Moodle, I can see that people, so only like this, they've only been like, oh, these are videos, no views for the playlist, obviously. But if I look at the videos that are in this playlist, the recordings, because I know some people miss classes, right? You know, you have some videos that haven't been viewed, 1 view here, 2 views, 5 views here, 12 views here, or something like that. I mean, this is a class of like almost 100 plus students, right? So the resources are on the Moodle, right? If you log into the CSC 4505 course here, you will find all of these things here, right? I see some comments here. I don't know if it's lecture 4 on Moodle only has 39 slides. Yeah, well, I'll update this because I keep on expanding. That's fine. I will update this. I don't think it has 39 though. I don't think we're being sincere here, but that's fine. What are the other workarounds aside from Pygame? I'd say Piglet, for instance, right, is one example. Tcint as well. Also, there are a number of Python libraries that you can use for windowing. You know, but the learning curve for Pygame is not that steep. I've used Tcint in the past. I've not used Piglet, but you can try out Piglet. I think in the last one of the things we did in the last lecture series is well, something simple really, but we attempted to install the Piglet package. The pip install Piglet. Sundays 13 is difficult because of church, but I don't know how we can do this here. What book are you using? I am using. Here's the thing. That's an interesting point here. The notes I'm using are here. Now the code is in. I'm using Len. Is it Len OpenGL or something? Len OpenGL has a number of resources, right, and tutorials. The only thing is, I think the code is in C++. So it's just a matter of converting. The only thing I'm doing is I'm converting the code which is in C++ here in Python ideally. That's it. And this I think was mentioned as one of the resources that I was going to be using, right? So if you notice here, OpenGL, creating a window, is what I'm talking about here. Except, let me just confirm here. I think this is in, the packages that are being used are completely different, and this is in C++ ideally. Okay? A wealth, a lot of useful resources on Learn OpenGL. You know, is that? At least 18 to accommodate everyone. I don't know. I mean, we can chat about this. Please have your course reps reach out to me with alternatives, proposals. But for now, we've tentatively agreed that we have class on Sunday and Saturday at 13. If you're going partying tonight, make sure that you don't overdrink. Otherwise, you'll miss class and you lose marks. Thanks, everyone. We'll see you when you see me, which is tomorrow at 13. Bye.